Hi, this is a short version of a talk I gave at an EAG workshop in Copenhagen in June 2012. The workshop was on open source EMP software, and that's mostly geophysical software. The audience was mostly geophysical developers from academia and industry. Talking about open source mobile software, open source is a kind of a philosophy for Agile. Our blog, our wiki, we just did a book on geophysics, and the software that we do is all permissively licensed under Creative Commons terms, or for the software, BSD style licenses. And why mobile? Well, we think mobile is it's fun to use, it's everywhere, the devices are inexpensive, it's a lightweight platform but massively powerful with beautiful screens, and they're just fun to share, a bit social and so on. Some people feel like there are some disadvantages with some of that it's frivolous and cheap, and really the platform's meant for games. But when you look inside these things, they're so powerful now, packed into this 82 cubic centimeters. That's 24 times smaller than my laptop. There's all sorts of goodies, quad-core 1.4 gigahertz processor with a gig of RAM, lots of storage, loads of different sensors, accelerometer, gyroscope and so on. Even the cameras are sensitive to infrared light, like most digital cameras. So they do have sort of superhuman capabilities, and of course the compute is superhuman as well. This is a little graph showing how supercomputers have improved over time from 1940 to 2010. Measuring performance here in floating point operations per second. That's the blue line in supercomputers. The green things are Intel CPUs, so the sorts of things you find in laptops. The Core i7 is a pretty new processor. And you can see how those have improved over time. And then marching right behind them are the mobile devices. So these are all Apple chips here. But you can see how with the iPad 3, we're basically we've got the performance of a sort of late 1980s supercomputer and an Intel Xeon chip. So really we can start thinking about doing serious science on these things. And when you see the video capabilities with the graphics that these chips can handle, you should check out the demo online. There's you'll find a video for this VJ software on iPad, and it really is incredible what you can do. In this case, merging two pieces of video with sound. So the chips are very capable. Now, of course, there's iOS and Android are the two sort of preeminent operating systems on mobile. Android sort of accounts for a lot more devices, but the devices are quite. There's a very large spread of different manufacturers, different physical devices, tablets, some with buttons like this, some with buttons like that. iOS is much more homogeneous, and in a lot of ways for developers that makes it easier to develop on. So hence quotes like this: Android delivers less gain and more pain than iOS. Developers are flocking to iOS, hoping to build the next, Angry Birds or Instagram. 18,000 software development kit downloads in the first quarter of this year alone. Now we keep a list of mobile geoscience apps that we know about on subsurfwiki.org. Please check it out if you're interested in trying some pieces of software, or if you know about any others, please add them. It is, it's a wiki. You're welcome to edit that page. Here's a piece of sort of seismic-oriented software that I know about on iOS, iPhone and iPad, called Pocket Size. It's $20. I haven't actually tried it out. I think the price is a bit steep for the functionality, but I love seeing this stuff out there, so I hope there's more to come. Here's one of our apps. It does volumetrics. And you could say, well, I can do that in my head. Well, maybe not in your head, but I can remember that equation, no problem. I can just pull out my calculator and I don't need an app to do something like that. And fair enough. But what we like to think is we can actually tuck some expert opinion and judgment and things like lookup tables and cheat sheets into the app, hopefully as seamlessly as possible, so they don't kind of get in the way. but when you can't remember what geometric factor is or how it works, or you can't remember the equation for B sub g in a gas prospect, the app can come to the rescue. You'll see in that little orange box on the screenshot there, we're also able to pull in things from the cloud, right? So that's the oil price coming in from Yahoo Finance, and that saves you having to go look that up, because it's up to the minute accurate data. And we can pull all sorts of things from the cloud along with data like that. We can pull in YouTube videos for tutorials, online help from the wiki. We can pass data back and forth with other apps. We can store things on the phone in a database. We can use the email. If it was relevant or useful, we could access the camera, the GPS in the phone. It's a very rich environment for developers and potentially, hopefully for users too. Here's another of our apps, AVO, takes some rock properties and it does a plot of the reflectivity with offset. It's a pretty simple little app, but drawing the graph was tricky for us. We didn't know how to do that, and it turned out that we actually didn't need to do it because Google have this API, or application programming interface, for drawing graphs. So actually all we had to do was build this pretty horrific looking URL, which basically just contains a lot of parameters for the graph we want, axes, colors and so forth, and actually includes the functions that we want to plot, in this case the Shuey equation and Aki-Richards equations, and in this case with the blue line is with brine, and the red line is with gas. And I highlighted one of the Aki-Richards equations there in red so that you can sort of pick out where that is in the URL. And it may look a bit clunky, but actually building text like this in the app is quite easy. And we thought, well, wouldn't it be awesome if we could do the same thing but get Seismic in? So earlier this year I sat down with a developer from nthought, Python programmers from Austin, Texas, and we built a web API for seismic models, in this case a little wedge model. We can also do offset synthetics, and again all we're doing is building a URL, so we're passing in a bunch of parameters just in plain text to the app, which is on the web, so it's on a server on the web, and it passes back a little plot. Now we've also built a little interface for it. I'm not going to make any claims that this is a great user interface or anything. It was really just a proof of concept, but it may make it a little easier to explore the API. You can put numbers into boxes here and have pull down menus and so on, and as you can see in the middle there, it builds the URL and then pulls in the plot. So what's the architecture like? Well, in the middle there is the browser view. That's what the user would see. On the top right there, that's the bit, it's this Google App Engine. Now what that's doing is building the interface, building that little form to fill out, and then making a URL and putting up the plot in the browser there. Google App Engine is fantastic, handles user logins, persistence of data, you get a little database, it's completely free, it's totally scalable and very easy to use through the App Engine launcher that you see on the right there. But that's not actually doing the work. The Python program that we built that builds these little plots, it passes the URL and makes a little plot, that's sitting on an Amazon EC2 server, which is basically just a Linux box on the web that sits in West Virginia somewhere, and you get access to it through an SSL terminal, which you can see on the left there, and it's running the software and doing the actual serving of these images. Now, the cool thing about it being a Linux box is we can potentially load Madagascar on there. We could be doing, right now we're just doing convolutional model, but there's no reason why we couldn't add finite difference. We could add ray tracing. We could do state-of-the-art stuff on that platform. SegWiPy, you can read SegWi files. Maybe we could put up some public models there so that you can explore those through the web API. All this stuff's on GitHub, github.com/agile-geoscience. So agile-geoscience is, you'll find our mobile apps that you can play with. You can download them, they're open source. You'll need to do that in App Inventor. MIT App Inventor is the platform we use for developing that stuff. So they're not sort of pure Java or anything. And then this modeler tool, which is the web API for gathers and wedge models and so on. welcome to go and explore that. If you're a developer, please get in touch, and if you fancy contributing, I'd love to talk to you about things we could do in there. We definitely need help. So in summary, openness is a thing that we do at Agile. We get a kick out of it, we enjoy it, we think it's good for our company, we think it's good for the community. We love mobile because it's everywhere, it's easy to use, it's accessible, and we want to help put some expertise in people's pockets for those times in meetings and so on when you just need a quick answer. We think they're absolutely powerful enough for science now, and the web is a big part of providing some of that power, through things like web APIs, which we'd like to keep as open as possible to help us and others be platform independent. You can access a web API pretty much from anywhere, from any kind of app, whether it's on a desktop, laptop, mobile interface, it doesn't matter. So they help you be adaptable that way. And the openness, I think, can help us build something together as a community. So we're really looking forward to seeing if we can pull that off or not. And either way, we'll learn something. I hope you've learned something a little bit, maybe. Go check out that list of apps, give some of them a spin. Or if you're a developer and you fancy having a chat about what we can do with web APIs, then please give us a shout. We'd love to talk to you. That's it. Thanks so much for listening, and have a good one. Bye.